Okay, consider this jump. Wouldn't it be nice to know what velocity is required to land this jump? And for this, I have now implemented a velocity heat map, which shows, for example, with starting tick 13, which velocities land the jump. So we have now this velocity heat map, and the green parts show which velocity would land it. So first of all, we have the axis, vz, and vx, which is the velocity. And if I hover over it, you can see v0 is the starting velocity. And for example, here we had, let's take something like here, minus 0.1784 and positive 0.006. So if I click this, it will apply this to this tick. And now we will see, or we can see, that it lands the jump. And this is essentially the velocity heat map. There are many velocities that are humanly not reachable simply because they're too fast, for example, this one. And we can also take a look at the 3D map. The 3D map is also clickable, and it shows where the valleys are. And the lower a valley is, the better the solution is, kinda, because we have the solve for, which is the objective. In this case, maximize the x value, and that is pretty much get this tick as max on x as possible. And right, so for example, here we are quite far away from, or very close to the edge of this block, and here we are quite far into this block. So, but for those that maybe already know parkour, you might consider this a bit of cheating, because of course this velocity is not reachable, and furthermore, we are stepping quite far out of the block. Because of the high velocity, we are now able to pass this pane quite earlier, like probably one tick earlier, and that allows us to land closer. So what you could also do is, instead of selecting the tick before jumping, we can select the jump tick, and now this locks the position here, and now we must work with the velocities from this position onward. So this is way more of a simulation of what the jump actually does or looks like. So if we now find the velocities again, we can see a much smaller amount of velocities that work. And of course, you can scroll in as far as you want, and I think there are quite some interesting fractal-like things happening in here. You can also see the 3D view again. And now if I click on here, of course, the player starts in the air. So if I now click on here, it still lands. The player can, for those that don't know that, stand one tick in the air, which is why head hitters are possible, because you run one tick and jump after that from the air. So this is a valid position. As we saw, the jump itself used that position. Here we are still on the block. This is the one tick that can be in the air where you can still jump. And we are using that essentially to find the velocities from. So now you might wonder, okay, how precise can we go with this? Because the butterfly Neo is still somewhat of an easy jump, you could say. Let me replay this real quick so you get an idea. Stupid weather. This is what the jump looks like. So it's quite easy. So let's take a look at the head butterfly Neo, which is one of the hardest and most precise jumps, at least that I know of. And let's take a look what the velocity heat map shows here. So let's find velocities. And the first thing you will notice, if you know this jump, wait, there's quite a lot green. This jump is so precise. Why is there so much green? If I select, you can probably already tell why. Once again, it uses velocities, and this time at this here, positive 0.55, which is just unachievable. And this allows the solver to, again, step ahead on the tick, on the first jump tick, and this saves pretty much one entire tick on the solution. So let's take a look at what happens if we start from the actual jump tick. Because, and this needs now some background information, the first tick is never able to pass beyond this head. There's just not enough velocity. If we look at the first tick right here, we can see that Z is perfectly aligned, incredibly close in front of the head. In this case, 0.000001 in front of this head here. 4930.050 is exactly where this head starts, and we are incredibly close in front of it because we can't pass it on the x-axis. We must stay in front, and only the second tick is able to pass it on the x-axis. So this tick can move forward. And what this essentially means is you can't just increase the velocity here onto the z direction, because you will just crash in the head if you go any faster than this. But you are also not able to go any slower, because as you see, this is incredibly close aligned as well at point 2, which is this side, the x side, and on this side, 950 on the z side. And we are, again, e-6 or something away from colliding here. So if you go any slower, this tick will not make it. If you go any faster, this tick will collide. And this is why, if you start solving from here, which is, as you see, if I replay this, alleged starting position, way more accurate in trying to figure out the velocities, or it incredibly decreases the search space we have. So also this jump only lands by e-4, 0.0001 in this case, so it is also incredibly precise on the landing. But what happens now if I start searching from tick 33? Let's see. And what we can see is almost all of this is red. Like if I scroll around, also the green bubble goes away, but there are solutions, as we already saw teasered. But you need to zoom in incredibly far, and now we can see solutions. And these solutions, if you hover around, are only changing the velocity by e-4. And for that, even if I click on this now, of course I fall down again, so place the block, you can stay in the air. So let's select the landing block right here. This is the landing block. And now you actually have to look at the coordinates and see that something changes. So if I click, let me find, it's really hard to click. You see the numbers change because the velocity is only tweaked very minimally. And you can see the 3D view is pretty much, you can't make this except at very precise velocities. So you might wonder now, okay, that's good. Now we can figure out the velocities to land a jump with, but what now? So the idea that I have is that I sample this velocity heat map over a range of positions, then overlay those velocity heat maps, and there where the velocity stays green essentially means you're able to make this jump inside or from this position if you hit the velocity. And I can then use that information to brute force inputs, ideally while staying on the block as expressed as a constraint again, then hit this band with the velocity and also hitting the velocity itself, like hit the position and the velocity. And if I'm able to brute force that, then I can solve the entire jump, because everything after that is already solved. And that is essentially where I want to go with this. But I also think this tool could be quite useful for seeing where the limits are for certain jumps, maybe for jumps that are impossible, and also figuring out, okay, how much velocity would I need to make this jump actually? I think that's pretty cool.